And hello all, Mr. Cowan here to help you with today's e-learning lesson. We're going to talk about lesson 7.1a, rational exponents. So let's get into it. We're going to start with the page, again, 7.1a, rational exponents. This is the notes page. You got SAT warm-up, some problem string here, and some practice on the back. Now, I will advise you to pause for just a few minutes, see what you can do with these two SAT warm-up problems. If we have time, if it's not too long of a video, we will come back in a moment and do answers later on. All right, so our goal today, our objective is I will write exponential expressions in multiple forms, multiple representations. And as always, we try to simplify when we can. So if you look in the blue balloon, think about learning like a hot air balloon. We start at the bottom. What have we learned already? We've learned about laws of exponents. We learned about simplifying expressions. We learned the basics of powers. Goal today is going to be to rewrite things like this in simplest form. And sooner or later, where are we heading up in the sky? We're going to try to do exponential, but algebraic equations, not just numeric, but numeric and variable. Now, speaking of expressions, powers, roots, etc. Let's review the vocabulary. Remember, this whole numeric expression is called a power. A power is made up of a base. The base is the number, the factor that is being repeatedly multiplied by itself. The exponent is what tells you how many of those are repeatedly multiplied. Meanwhile, let's pop down to a root, please. A root, remember, is what number is multiplied by itself. This is the radical symbol, the black symbol that goes like almost like a check mark and then over the radicand. Radicand is the number underneath. Index is the number of times we're looking for the root to be repeatedly multiplied. So keep that in mind. If you do not see an index, basically what that's going to mean is that the index is going to be a 2. I don't know why they do that, but that's the way it is. What else? A factor. Remember, a factor is a number that goes perfectly into another quantity without having a remainder. So for instance, if you think about the number 20, 2 is a factor of 20, as is 10, but 12 is not. If you divided 12 into 20, there would be a remainder. And prime means a number that can only have exactly 2 factors, 1 times itself. So for instance, 2 is prime, 2 times 1. 10 is not prime, 10 is composite. So 10 can break down into other prime factors. In this case, 2 is prime and 5 is prime. Again, 5 only has precisely 2 factors, 1 times itself. If you would rather do upside down division, which is how I taught this in 7th and 8th grade, think about dividing. And I always start with the first few prime numbers. 1 is not prime, by the way, folks. 1 has only 1 factor, 1. 2 is prime, 3 is prime, 4 is not prime. 4 is composite, 1 times 4 and 2 times 2. 5 is prime, 6 is composite, 1 times 6 and 2 times 3. Again, composite numbers have more than 2 factors. 7 is prime, then 8, 9, 10, all composite numbers. 11 is the next prime, followed by 13. I wonder if you know the next one. Be 17, and so on. What I always like to do when I'm trying to break down, whether you use a factor tree or upside down division, is I just go in order. So if you find these to be important, go ahead and write those in your notebook. Keep those in mind. Does 2 go into 20? Yes, it does. 2 times 10. Does 2 go into 10? Yes, it does. 2 times 5. Oh, and 5 is prime. Some people even circle those. So if you look at what's called the prime factorization of a number, it is the list of all factors that are prime, 2 times 2, which of course is 4 times 5. This is what we would call a prime factorization. Keep that in mind as we go along. All right, if you'd like to pause, go ahead and title your notebook. A lot of our notes will be online, but you always need some notes. This is probably going to be a 2-day lesson entitled Rational Exponents. Pause. Come on back when you're ready. So we're going to start off with some basics. I'm going to flip my computer. Hopefully it doesn't be mean to me. Our goal, writing each expression in multiple forms, simplifying if possible. So I have no doubt that many of you are going to look at the square root of 4 and say, hey, I know that one. I know it's 2. But could you write it in another way? So for instance, can you keep the radical symbol and rewrite 4 as the product of its prime factors? Or rewriting that as the square root of 2 squared. Now again, recall please, little disappearing ink, if you don't see any number above the radical symbol, the index is 2. You can write the 2, you cannot write the 2. Oftentimes I will. This might furthermore be written as I wonder if you remember that we can rewrite a radical as a rational exponent. How many of you are going to know that? And of course, then one could also simplify that to say this is 4 to the 1/2 power. Now I'm doing all of this because many of you immediately pop to the 2, but some of us need that challenge of writing things in multiple ways. And so I'm going to challenge you as we go through the rest of this problem string. Keep trying to come up with other forms, other representations of the root. For instance, let's do the next one together, the cube root of 8, which many of you again will say, hey, Mr. Callan, that's the same thing as 2. But a reminder, please, could we rewrite this in another way? Well, 2 times 2 times 2, cube root of that, which could be written as the cube root of 2 to the 3rd power. And recall, please, that powers and roots cancel. Perhaps that's why we noticed that 2 is the ultimate root. I wonder if you could write it like this above. So for instance, we could write 2 to the 3rd, but now because the index is 3, that would be a 1/3 exponent. And then you could furthermore write that as 8 to the 1/3. Now, again, I wonder if you can see where this is going to be heading for future problems. So, keep that in mind. I'm going to ask you to pause your video. Try the next two, please. Multiple representations. Pause your video. Come on back when you're ready. 4 through to 16. Are you seeing a pattern? Meanwhile, I'm going to rewrite this, keeping the radical symbol, keeping the index of the 4th root, and write 16 in its prime factorization. Gee, what number could we multiply by itself repeatedly 4 times to be the same as 2 multiplied by itself? Well, that would of course be 2. But were you able to come up with another way of writing that, continuing with the radical symbol and the index of 2 to the 4th power, or writing it as 2 to the 4th power to the 1/4? Or, dare I even say it, 16 to the 1/4? And again, I wonder if you're seeing a pattern here. Meanwhile, for the next one, again, no index, which means the square root, and many of you already know that's 5. Did you in fact write the square root of 5 times 5? Or did you write the, square root? Square root of 5 squared, or 5 squared. Now, since this is an index of 2, changing that to a 1/2 power, or 25 to the 1/2. So pause your video if you need, rewind, look at how they're similar, look at how those problems are different, and let's carry on with the next two problems. Pause your video and come on back when you're ready. So let's go with this. Cube root of 125. Mr. Callan, that's still 5. Indeed, it is. What else could be similar? Well, we could write this as the cube root of 5 multiplied by itself repeatedly. How are those problems similar? How are they different? Well, this one's going to have an index of 3, 5 to the 3rd power. Or, oh man, 5 to the 1/3, 125 to the 1/3. I wonder how many of you took this and remembering the law of exponents, that when we take the power of a power, we can multiply those exponents. And you would write this. which could also be written as 5 to the first power. There are so many different representations, all leading you to say, but Mr. Cowan, you said simplest form, and both of those ultimately have a root of 5, which is true. How about the next one? Pause if you haven't gotten there. Come on back when you're ready. So the fourth root of 625. Maybe some of us are having a hard time coming up with the answer right off the bat. So what if you went ahead and just separated it out? I'm going to do upside down division here. Or you can do your factor trees if you want, but I like upside down division. Does 2 go into 625? Remember those prime factors, 2, 3, 5, 7, 11, 13. And usually you'll catch them by then. 2 doesn't, 3 doesn't, but 5 does. And 5 goes into this 125 times. Now, is 125 prime or composite? Well, I believe 5 goes into that one. And 5 goes into that 25 times. And you can see ending with a 5 again. 5 will be another factor of this. Oh, would you look at that? In other words, if I wrote this in expanded form, the fourth root of 5 times 5, gee, what number multiplied by itself 4 times would be the same or equivalent to 5 multiplied by itself 4 times? And naturally, that's going to be a 5. I wonder if you could also write it as a power of 625. Seeing that we have a fourth root here in the index, you could write it as such. Square root of 144 you might find interesting. So again, having a hard time coming up with a perfect root. And some of you might notice something at this point. So let's see if we can find the second root of 44. I'm going to go ahead off to the side. Now, I did the other one as upside down division. Some of you much prefer factor trees. So I'll do this one as a factor tree. Does 2, remembering our prime factors up here on top left, does 2 go into it? Well, surely it's even. Now, 2 is prime, but 22 is composite. And being even, 2 goes into that 11 times. Oh. Now, this is going to be interesting, ladies and gentlemen. Noticing how this problem is different from every other problem that we worked on. Up at the top, we only had repeated 2s. Then we had repeated 5s. But this one, it's not the same number over and over again. However, could we do a little karate chop, break it up, and say, what about the square root of 2 times 2 multiplied by the square root of 11? Well, what number multiplied by itself twice is the same as 2 times 2? That would be 2. But unfortunately, the square root of 11 cannot be simplified. Now, as a reminder, you're always welcome to put the dot to exemplify multiply, but it's not necessary. So with that in mind, I got a couple different ways of writing this in different representations. We got the square root of 2 times 2 times 11. We got 2 times the square root of 11. Perhaps you would even write 2 times 11 to the 1/2 power. All are going to be equivalent, but I wonder if you can spot the fact that 2 times square root of 11 is simplified, where the square root of 44 could break down. I'm going to get rid of those because I really want to emphasize 2 times the square root of 11 is what we would call simplest form. Now, can you take from that and learn for the cube root of 16? So I'm going to ask you to pause your video, see if you can simplify, even if it doesn't have a perfect integer root. Let's see if you can simplify that. Pause, come on back when you're ready. So if we were to go ahead and stretch out 16, we would end up with the prime factors of 2 times 2 times 2 times 2. Now, at this point, you can see that we have the cube root, you could even write it, the cube root of 8 times the cube root of 2. There's an equivalent form. But most of you are going to say, well, the cube root of 2 times 2 times 2 is going to be 2. But we still have something that must be left over in the radicand as a radicand. And so the final answer, with or without the dot, is going to be 2 in simplified form, 2 times the cube root of 2. Yes, you could also rewrite that in other ways, 2 times 2 to the 1/3. Or, seeing that when you multiply powers, you add their exponents. 1 whole plus 1/3 is 1 1/3, or 4/3. Or, 16, which is 2 to the 4th power, to the 1/3 power. All those equivalent forms, this is what we'd consider simplified, but I'm hoping you start seeing those patterns here. Again, if you need to, rewind, watch what you need to rewatch. Let's go on to the next part with maybe the most important piece, and that is the connection. Can you connect the square root of 4 to 4 to the 1/2? The cube root of 8 with 8 to the 1/3. 16 to the 1st with the 4th root becomes 16 to the 1/4. 25 to the 1st, the 2nd root of which, 25 to the 1/2. And I hope you're starting to see even 125 or 625. If you wrote 625 to the 1st power with the 4th root of such, and maybe at this point you're seeing what we already got a brief glimpse of last semester. If you want to rewrite the mth root of x to the n power in base form, in exponent form, note to yourself, the base does not change, but for the exponent, you could write n over m. Again, where n, the numerator, is going to be the power, the exponent, and m, the denominator, is going to turn into the root. Now, if you need to pause, make sure that's in your notebook. Liven it up, put some color in there. You can grab some highlighters, focus on that pattern as we continue. Pause and come back when you're ready. All right, so we're going to do a few of these together, then you're going to continue on. Starting with number 3, I'm going to make this a little larger. That's not larger. Yeah, that's better. Goal is to write each expression, but this time as a radical expression. So we're going to need to rewrite this in radical form. If the expression is equivalent to an integer, then go ahead and write that integer. All right, so let's begin. I'm noting that 49 is the base. Don't touch the 49. I'm going to try to keep the color scheme, if I remember that, green and purple. All right, let's try it. So green being the numerator, that's going to be 7, is going to be the exponent. Purple being the denominator, so it's going to be a 4th root. Now, I cannot do, neither can I do 49 to the 7th power easily offhand, nor can I do the 4th root of 49. If I try to break up 49, I can do a 2nd root, but I can't do a 3rd root or a 4th root. So I do believe that's going to be as good as it gets. Pause, do number 4 real quick, and come on back when you're ready. Now, for number 4, I'm going to go ahead and shrink this a little bit. Leaving 100 as the base, you could write the 3 as the exponent. You could write the 2 as the radical. Whether or not you write the 2 is up to you. But please note that we can easily do the square root of 2, which is 100. That's 10. And then 10 to the 3rd power is going to be 1,000. So it says if it's equivalent to an integer, we should be able to say either one of those and then the fact that this is going to be 1,000 easily. Whereas we can't quite do that with the 4th root of 49 to the 7th power. Now here we're going to go backwards for number 5. So it says write each expression as an expression with a rational exponent. And again, if it's equivalent to an integer, let's go ahead and write that. So I'm going to go ahead and I'm going to note that 243 is the base. We're going to see that the exponent is going to be the 3, so that'll be our numerator. And our index is going to be the 5th power, that's going to be our denominator. Now, good news for this one, folks. The 5th root of 243, watch this. 2 does not go into it because it's not even, but 3 does, 81 times. 3 goes into 81, 27 times. 3 goes into 27, 9 times. 3 goes into 9, 3 times. 3, 4, and 5, multiplying 5 repeated. So the 5th root of 243 is 3. and 3 cubed is going to be 27. So our answer here is twofold. We're writing it both as a rational exponent, 243 to the 3/5, and because this one was so nice, we could actually simplify it to a lovely exponent. Pause your video, do number 6, come back when you're ready. Shaboom! This one also can be written both with a rational exponent as well as a lovely integer. Negative 216, note that negative has to stay with the 216, thus the grouping symbols are important. And exponent is 2, index is 3, 2/3 power. Meanwhile, the cube root of 216 is a lovely negative 6. And if you multiply negative 6 times itself, remember that the opposite of a negative times a negative, opposite of a negative is going to be a positive. All right, how about down below? We are asked to solve for n. Basically, we're just coming up with what is the rational exponent, excuse me. So I'm going to squeeze a little 1 right there, and therefore that would be 1 as the numerator. The radical symbol, I should have used purple, is going to be 6. So really all we got to say, you can write it simplified, you can write it solve for n, but we're looking for the 1/6 power. In this case, numerator is 2, denominator is going to be the index. So the third root of a squared is the same as writing a to the 2/3 power, and we can do the same thing here. It is sometimes an improper fraction, which is perfectly okay. Again, we see the exponent is the 6, that'll be the numerator. Index is a 5. So the 5th root of a to the 6th is the same as a to the 6/5. All right, pause your video. I want you to do 10 through 17 and come on back when you're ready. Check your answers. Put a little star, circle, big old question mark next to anything. And if you do have a question, it's better to write that question out so you don't forget it before you get back to class. Folks, we're going to wrap up with the challenges where we're heading in the next couple days. I don't need this to be perfect, but I do want you to pay attention. How can we then expand and simplify if we have both numbers and variables inside the radical symbol? So let's just do a couple of these, and this is going to be a little fast, a little uncomfortable, but don't sweat it. First thing I'm going to note is there's no number outside this, so it does mean a second. Therefore, I'm going to go ahead and I'm going to try to expand using some upside down division or your factor trees. That's up to you. 2 goes into 20 10 times, and while 2 is prime, 10 is composite. 2 goes into 10 5 times, and I do believe we have now come up with the prime factorization of 20, which is equivalent to 2 times 2 times 5. X squared is equivalent to x times x, and a y down there. Now, can we go ahead and rewrite this as something times something? It's not going to be perfect, but I note here, what number times itself is the same as 2 times itself? Well, that'd be a 2. I note here, what number times itself is the same as x times x? Well, that would be an x. Meanwhile, left over, the 5 doesn't have any pair. The y doesn't have any pair. So written in simplest form, we would say that the square root of 20x squared y is the same as saying, well, why would you write square root of 20 and the square root of x squared when you could write 2x multiplied by the square root of 5y? This, folks, is simplest form. Let's do another one. Cube root, 24 is the same as 2 times 12. 12 is the same as 2 times 6. 6 is the same as 2 times 3. I'm just going to go ahead and check this. 2 times 2 is 4, 3 times 2. And just to verify, 24's prime factorization is 2 times 2 times 2 times 3. Now I'm going to go ahead. You might not need to do this, but I'm going to expand out x to the 4th. 1, 2, 3, 4. And I'm going to expand out y to the 3rd. 1, 2, 3. So, can we simplify any terms on the inside? Well, wait a second. We're looking at a third root. What number times itself is the same as 2 times 2 times 2? That'd be 2. And it's almost like you can now cross off and forget about those 2's because we've just simplified the cube root of 8, which is 2. Meanwhile, take a look at x's. X times x times x. We can pull an x out. Now take a look at your y's. Y times y times y. So the cube root of y cubed is y. But unfortunately, we're not finished because there are still some leftover pieces to the puzzle. You cannot say that the cube root of this is equivalent to 2xy, because if you multiply 2xy times 2xy times 2xy, you get 8, which is not 24. You get x cubed, which is not x to the fourth. So these are not yet equivalent. We need the extra pieces of the puzzle. And is there anything in addition to the oh yes, we do have an extra x. Now those, my friends, are equivalent. The cube root of 24x to the fourth y to the third is the same, and one could even say simplified, to be 2xy times the square root of 3x. One more, and this one's going to be a bit more of a challenge, perhaps, maybe not. 8 is the same as 2 times 2 times 2. X to the seventh, 1, 2, 3, 4, 5, 6, and 7. Y to the third. Pause if you need to. Come on back when you're ready. Now there is a bit of a challenge here because you almost might have said the 2's. However, that is not 2 to the fourth power. That's 2 to the third power. So literally, you won't be able to pull those 2's out. Is there anything we can pull out? Well, n, 2, 3, 4, and some people even do this. So we can pull out an x, but nothing else. Interesting. So what we need is to multiply x by 8, x cubed, y cubed. Nothing else can be pulled out of there. It doesn't look simpler, but it is, because why write the fourth root of x cubed when you can actually pull an x out of that? Folks, I'm going to pause there. That's pretty much what you got for today. Don't forget to continue studying. We're going to have to, at some point, return to being in person, take our test. If I could point out then on the calendar. So we're gonna do the test tomorrow. We're gonna start it in the very least. Even if we have another delay, it might not be enough time to finish the test, but we'll try to start it and then get going and finish it up 28th and continue on with our new concept of rational exponents and simplifying expressions. That's what I got for today, folks. Take care, do well. Let's grow. See ya.